Alrighty, welcome back. Video 3 for topic 5A on insolation. So far, you should have watched the first 2 videos. If you haven't, you should probably just stop now and go back and watch those. You need that information to make sense of this. But we've talked about our 4 key dates, the angle of insolation, the intensity of insolation, the duration of insolation, all of those things. They're all concepts we talked about before, honestly. It's just there's a lot of new vocabulary in this topic, so you need to be familiar with all those. And remember that the angle of insolation is the single most important factor for determining how intense the insolation is. So the higher the sun is in the sky, the more intense the insolation, the sunlight is, and the warmer you're going to end up getting as a result. So, now I need to talk about that insolation when it gets to the Earth's atmosphere. The sunlight that gets to the atmosphere versus the sunlight that gets through the atmosphere and to the surface is not the same. The atmosphere acts like a giant pair of sunglasses for us, and it filters out some of those harmful rays. So, solar radiation reaching the atmosphere is affected in 3 possible ways when it gets to the atmosphere. And it sort of depends on what wavelength you're talking about. Different wavelengths are affected differently. Some pass right through and are hardly influenced at all by our bubble of gas around the planet. Other ones get completely roadblocked and don't get through at all. So different wavelengths are going to respond differently. So, first option is the wavelengths could be absorbed by the atmosphere. This equals about 1/5 of the total, 20%, depending on which way you want to look at it. And honestly, this is a good thing. You wouldn't think the atmosphere absorbing our energy would be that great. I mean, heck, it's wintertime. I could like it to be a little warmer. But the wavelengths that are absorbed include X-rays, and you wouldn't want to be exposed to X-rays all the time. Having a few brief moments of X-rays to look and see if you have a broken bone, that's okay. Being exposed to X-rays every time the sun is up for your entire life, well, it would mean your life was a lot shorter, so I don't think you'd appreciate that. And the X-rays are absorbed in the upper atmosphere, miles and miles and miles up, nowhere near you, so your exposure to X-rays is pretty minimal at the Earth's surface, thanks to it being absorbed. Ultraviolet radiation is also absorbed in the atmosphere, ideally quite a ways above the Earth's surface, and is absorbed by a substance called ozone. Now, you've probably heard of ozone before. It's not mentioned as much as it used to be. Back in the day, it was a pretty big topic because we sort of kind of accidentally tried to destroy the ozone layer, us humans. We use these chemicals called CFCs for refrigeration and for some other purposes, repellents and whatnot back in the day. And it turns out, we learned after a while, that CFCs are really good at destroying ozone. So we almost dug ourselves a pretty big hole there. Well, we did dig ourselves a hole, it's just we saved it in time, I think. And ozone, what's still there of it, and it's coming back slowly, stops ultraviolet or most ultraviolet from making it through the atmosphere. It stopped way up in the stratosphere. So quite a bit closer to us than the X-rays were, since they were stopped way at the outer edge. But nonetheless, ozone does a pretty decent job stopping it. Now, those CFCs I mentioned, it stands for chlorofluorocarbons. And the reason they were a bad deal, we liked them because on the surface of the Earth, they didn't really respond to much. You could use them as a propellant or an additive, and they were pretty chemically stable. But it turns out when you put them way up in the atmosphere, when they float away, ultraviolet light breaks them apart. It breaks the breaks a chlorine atom off from the CFC molecule. That chlorine can then stick to ozone. Chlorine by itself is really, really lonely, looking for a friend, so to speak. And so it bonds to ozone, which then takes one of the oxygens off from the ozone. Now you have chlorine monoxide, and you have just plain old oxygen, which isn't bad, floating around the atmosphere. And then when that chlorine monoxide runs into another oxygen, the oxygens like each other even better, and they bond, and then the chlorine's loose again, and it tears apart another ozone molecule. So, bad deal. Once we realized it was a problem, most countries agreed that, hey, we should not create more of these things. Every once in a while, there'll be someone who sort of breaks an agreement and does create some, but for the most part, we've stopped the problem before it became critical. There's still some thinning in the ozone layer, but it is gradually healing itself. All right, so we looked at this way back on the first day. You have your two graphs, one for the blue line being the energy that gets to the atmosphere, the yellow line being what gets to the Earth's surface. And what you could see, if we look closely, talking about X-rays and ultraviolet. X-rays and ultraviolet are both pretty short wavelengths, so they're on the left-hand side of the diagram. X-rays and ultraviolet will be next door neighbors on the chart. And you can see the sun doesn't give off a ton of X-rays. It's one of the lower things, but none of it, you notice there is no yellow line for X-rays. They just do not get to the Earth's surface. They're absorbed way up. Ultraviolet light, the sun gives off a fair amount of that. It's pretty up there, actually. But what actually makes it through the atmosphere, especially the really short, more dangerous wavelengths, is almost nothing. And then as it gets closer to the visible light range, there's some more of it, and that's absorbed by ozone in the stratosphere. So on page 14 in your reference tables, there's a diagram that looks kind of like this. It's not as pretty and colorful, but it's the same diagram, basically. And it shows the different layers of the atmosphere and their temperatures. Now, what you notice when you look at this graph is that starting from the surface and going up, it gets colder, then it gets warmer, and then it gets colder, and then it gets warmer. There's a back and forth thing going on here. And when the temperature changes, that's where it's called a pause. So like the tropopause, stratopause, mesopause. And those different layers happen because in these different layers, like in the stratosphere, for instance, ozone absorbs ultraviolet light that causes the temperature to go up. In the mesosphere, not much is absorbed, so it gets colder. That's where you have the coldest area in the atmosphere, the better part of 100 below in the Celsius scale. In the thermosphere, that's where gamma rays and X-rays and really super short wavelength particles are absorbed, and that's what makes it so warm. So the temperature zones are caused by different wavelengths being absorbed in them. Now, we live in the troposphere, way down at the bottom, and that's where all weather happens. That's where water vapor is. And our heat mainly comes from light hitting the ground giving off heat energy, and that heat energy being trapped in the troposphere because of the wavelengths it has. Here's the one from the reference tables. Like I said, not as pretty, but still very, very much the same. You have your different temperature zones of the atmosphere. You have the altitudes listed in kilometers and in miles, and the key temperatures at the turning points and the pauses here are labeled as well. The diagrams, this diagram particularly, is usually used for questions where it's very factual. You just have to look up what is the temperature at a certain height, or what is the name of the temperature zone you're in at 30 miles. So it's pretty factual based stuff. If you know this is here and you can read the diagram, you'll be good to go. So pauses are the boundaries between the layer. Alrighty. Lots of extra arrows. Don't feel like talking about them. All right, number 2, the second option. So some wavelengths, quite a few wavelengths are absorbed, especially the shorter ones. Option 2 is some of the energy is reflected or scattered back into space. When you look at the Earth from space, one of the things you notice is that we have a very active atmosphere. You see white cloud tops, very bright white cloud tops, and that's because they're super good at reflecting light. And so they make images really vibrant. The poles with their snow also reflect a fair amount of light. So about a third of the total, a quarter of that is by clouds, the rest of it's from the surface. Lighter colored surfaces are going to reflect more. Water is not very reflective. If you look at the oceans from space, when you see a satellite view, they appear quite dark, except in the occasional place where sunlight can get to the bottom and then bounce off the sand. Some Caribbean beaches and whatnot look pretty bright blue. But for the most part, the Earth's surface, forests are pretty dark. Sandy places, it's a lighter color. Snow is very light. And how reflective the ground is a thing called albedo. Not a term we need to worry about in earth science anymore, but if you ever, by some chance, they're talking about the albedo in a question, they're talking about how reflective the ground is. Now, another thing that we often overlook are these little things called aerosols. Now, an aerosol, like you can buy aerosol spray paint or aerosol adhesives, or anything that comes out of a can is probably called an aerosol. And aerosol just means it's a tiny little particle that's going to be able to float around the air. Dust, pollen, those are aerosols. Those are natural aerosols. So aerosols in the atmosphere can also reflect a fair amount of light. We've had some pretty bad forest fires in the United States. Australia's had some really bad forest fires in the past few years. And smoke from forest fires would count as an aerosol, or from a volcanic eruption. Luckily, knock on wood, we haven't had any bad ones of those, but they also put a large amount of aerosols out, and that can block light from getting into the Earth's surface. Now, light coming in, when you have more aerosols, it blocks more light from getting in. As a result, when the concentration of aerosols goes up, the amount of energy getting to the surface goes down. If you have a whole bunch of smoke from a fire or ash from a volcanic eruption in the atmosphere, it's going to have a cooling effect on the ground beneath. The longer it's there, it means less light's going to get in, less energy is going to get in, and it's going to cool off. And number 3, we have absorbed by the Earth's surface. This is the part that really is a big deal for humans because this is where we get our energy from. Of all the energy that gets to the Earth from the sun, only about a half of it actually gets through the atmosphere without being absorbed or without being scattered or reflected. So roughly a half gets to the surface and is absorbed by the surface. Once the ground absorbs that light, it can then re-radiate or give off heat energy. So the Earth does not give off light on its own. We give off heat energy because we absorb light. Some of the energy is used to heat up the material. And when it's given back off, it has a longer wavelength with less energy in it. And it's given off as infrared. So you can't really see it, but you can certainly feel the heat being radiated off the ground. So, to summarize here, about 25% is scattered and reflected by clouds. Roughly 4% is scattered by aerosols and gas molecules in the air. 19%, roughly a fifth of the total, is absorbed by the atmosphere, especially those shorter wavelengths like X-rays and ultraviolet. On average, 5% is reflected by the Earth's surface. That can be almost nothing from the oceans, or it can be 90+% if we're talking about a snow-covered field. So that overall is the average for the Earth's surface. And so just shy of 50% is absorbed by the Earth's surface and re-radiated as infrared. So infrared heat re-radiated from the Earth's surface could potentially just completely leave and go back to space. If that were the case, it would leave us frozen and cold, and the Earth would not be a great place to be. Luckily, in the lower atmosphere, there's a couple of really important gases that absorb heat before it can go back to space, and it keeps us warmer near the ground here. And these are not exotic, crazy gases. These are pretty commonly found things. The first one is carbon dioxide, CO2. The second one, definitely very common, is water vapor. So those two are very, very important gases for absorbing heat energy before it can go back to space. So the neat part is they both let light pass through from space to get to the ground, but they don't let all the heat back out. Now, as a result of that, we get what's called the greenhouse effect. Now, the greenhouse effect it's called that because it acts kind of like a greenhouse. The greenhouse effect is not caused by greenhouses. It's the fact that the atmosphere acts like it. If you've ever been at a greenhouse when they're picking up plants in the spring, for instance, it can be pretty cold outside, but it's nice and warm inside because the plastic or glass on the outside of the greenhouse lets in light, but when heat tries to get back out, it has a hard time penetrating the plastic cover. And our atmosphere acts the same way. It lets in visible light quite nicely, the visible light range, but when heat tries to get back out, some of it does, but a fair percentage of it gets held near the surface and it keeps us warmer than we would be otherwise. The greenhouse effect is a good thing. Without it, we would be frozen and the Earth would not be habitable. So, solar radiation comes in, gets to the ground. Some heat's reflected, some heat's re-radiated. Some of it gets out to space, but because of clouds, because of water vapor, because of carbon dioxide in the atmosphere, there are other ones too, like methane is a good greenhouse gas, that keeps heat near the surface. Now, often you hear about the greenhouse effect in a negative light because of the fact that we have polluted the atmosphere, especially since the Industrial Revolution, very heavily. We've dug up carbon compounds from the earth, carbon-based fuels, coal and oil and such, and we've burned them, tons and tons and tons of them, and as a result, there's way more carbon dioxide in the atmosphere than there would be otherwise. So the greenhouse effect is working too well these days. Global warming is a result of, at least in part, of the greenhouse effect. And so we have to be careful not to overdo it. If we do have too many gases in the atmosphere that capture this heat, the Earth's average temperature is going to rise, and then we're going to have issues. Probably the best example of runaway greenhouse effect is the planet Venus. We mentioned this before Christmas. Venus is a little bit closer to the sun than we are, nowhere near as close as Mercury, but it's the hottest planet in the solar system because the greenhouse effect is very efficient there. As a result, it's hot enough on Venus to melt lead. It's it's like 800 degrees Fahrenheit on the surface of Venus. No one's predicting that for here, luckily, but a few degrees warmer is still going to cause us great problems. All right, so back to this chart. When we look again, the dips weren't labeled before. You can see a whole bunch of dips in the yellow line. Those are the wavelengths, the specific wavelengths, that water and carbon dioxide absorb. So when the energy comes in from the sun, it doesn't make it to the surface because they absorb it first. And likewise, when the energy tries to leave again, those specific wavelengths are absorbed. And those are all in the infrared radiation range. So, because of the greenhouse effect, the Earth's nighttime temperatures stay pretty nice because when the heat from the day tries to leave, the clouds and the water vapor at night hold it in. You've no doubt, or if you haven't, pay attention. The coldest nights of the year are usually those winter nights where there's not a cloud in the sky, it's perfectly clear out. There's not a lot of water vapor in that cold air, and so as a result, any heat we gained from our short winter days takes leave of the Earth, and it leaves us very cold as a result. So the clear nights are the cold nights. In the summertime, it's the same way. If it's very, very clear out, the heat from the day can escape back to space much better. The thing to remember, they use a lot of diagrams for these, and I will on the test. Shorter wavelengths come in. Shorter wavelengths can pack more energy into less space. When the ground absorbs that and gives it back off, it's a much longer wavelength that tries to get out. Longer wavelengths have less energy, and so they don't get back out as well, and that's what traps them near the surface. So short wavelengths in, long wavelengths get trapped and can't get back out. Now, here's just some data. When we want to see how much CO2 is in the atmosphere, we try and find a nice clean place to do it, and one of the most remote places on the planet is the Mauna Loa Observatory in Hawaii. Well, hard to speak today. And it's a mountain top, old volcano, in the middle of the Pacific Ocean, as far away from most of humanity as possible. And here are the CO2 levels measured at the observatory from the 1960s through basically now, May 2019. And you can see a definite increase. The numbers have gone from in the mid to low 300s to now about 420. The units are parts per million. That just means for every million parts of different air molecules, 420 of them now are going to be CO2. Doesn't sound like a lot, but it's higher than any time in the recorded history, basically, of Earth, at least in the last million years. So, let's see, another one. This one goes back further. Now, this one uses ice core data before 1958, so we can dig up ice cores from Greenland and Antarctica, pull the bubbles of air out, so those bubbles were trapped many, many years ago. We can analyze what the air was like from those bubbles in the ice. So that's where those numbers are coming from. And you can see, prior to the Industrial Revolution, the parts per million was more like in the 280 range, give or take. And since the 1900s, since 1900 or so, the numbers have very, very drastically gone up as the Earth's population has gone up and we've burned more and more fossil fuels. Going, let's see, pretty much a similar thing. This one throws temperature on with CO2 concentration. Blue is below average, red is above average. And it kind of speaks for itself. CO2 concentration lower. The years are mainly below average. There's a few warm months in there for sure. And in the last 20, 30, 40 years, there really haven't been any years below average. We've been pulling the average up pretty steadily. So due to the increased release of greenhouse gases, scientists believe the average temperature of Earth is probably going to raise by about 2 degrees Celsius by 2050 compared to where we were around the year 2000. And that doesn't sound like much, but you have to realize that during the last ice age, when the majority of the northern hemisphere was under ice, we would have been under a mile of ice here. The global temperatures were only 5, 6, 7, 8 degrees below average in order to make that happen. So if temperatures are going up for the planet, the global average, by 2 degrees Celsius, that is not insignificant. That's going to cause ice to melt, sea levels to rise, climates to shift, and we're already seeing that to some extent. Sea levels have risen. Some island nations are suffering. Some parts of Florida at high tide are underwater. And we've certainly seen some pretty active hurricane seasons and changes in climate that we can probably attribute to this. Now, the problem with global warming and all these changes, we're living in it. So it's kind of hard to judge an experiment that you're living in. So you hear a lot of people saying, it's probably not real, this, that, and the other thing. But the reality is, if we follow the data, it sure looks like it's happening. And worst case scenario, if scientists are wrong, and they've been wrong before, probably not this time, but they've been wrong before, worst case scenario, the only downside of not polluting as much is that it costs a little bit. It does cost some money. It'll make things a little more expensive. But the downside of that versus if we don't do anything about it, it's going to be too late to fix it, and then we're really going to be in a world of hurt. So most scientists, the vast, vast, vast majority of scientists are on board with this. It's mainly politicians and people who want to make money that aren't for it. So it's just my little soapbox. So I'm going to go long because, as you probably figured out at this point, I'm quarantined again, so we're going to have some longer videos. Heat is transferred from the Earth's surface to the atmosphere by re-radiation of insolation as infrared heat. So what's that say? Well, there's a lot of big words there. So let's say this again. Transferred from the Earth's surface to the atmosphere by. So heat gets from the Earth back to the atmosphere by re-radiation of the sunlight. We absorb sunlight, the ground gives off heat, and that's what warms up the air. Another thing that can happen, sunlight can hit water, that water can evaporate. It takes a lot of energy to make water evaporate. We did that way back in the beginning of the year, but it takes crazy amounts of water, or crazy amounts of energy to make water evaporate. And as a result, it takes that energy into the air in the form of water vapor, its potential energy, until it changes phase back to liquid, then it releases that. But that can move energy over long distances when you evaporate water and have it blow off in the wind. And that heat is eventually released by condensation. Oh, here's another one. Land and ocean temperatures since 1850. Especially the ocean one is really scary because the oceans are hard to heat up, and they've shown a pretty significant increase even at depth in temperature. So that's kind of helping out our land average a little bit. The oceans aren't letting the land and air heat up as much as it might otherwise. When the oceans get warm, then nothing's holding us back. All right, so we won't worry about that right now. So you're going to have a worksheet assigned to you that should cover this material. And again, I'm not going to be in school through the 15th, I believe, this time I'm quarantined through. So there's going to be a lot of videos and worksheets that you're going to have to self-monitor and go through. If you have any questions, of course, you can always shoot me an email or give a comment on the classroom, and I'll be glad to get back to you. Thanks for watching.